The Italian pilot includes 1 office and 4 apartments. No BMS. We have solved this problem by installing a set of sensors and meters in the heating and cooling systems. Digital twin concept. From theory to reality. All the sensors and meters data are collected every 5 minutes. The outdoor weather data are captured from a nearby weather station.
Indoor data.
The data acquisition architecture pulls data from all the sensors installed in the pilot through a network that connects them all to a Raspberry Pi board. This Raspberry Pi runs an instance of Node-RED, an open-source platform designed to manage flows of data. In Node-RED, the Raspberry Pi queries every sensor in the network and formats the data so that it can be sent to an instance of Azure Riot Hub hosted in the IDP Twin portal. This whole system can be easily scaled, and the open-source nature of the tools being used makes it easy to maintain and replicate.
Outdoor data.
The data comes from a weather station located 200 meters from the pilot building. Temperature, relative humidity, wind speed and direction, etc. A script in Python has been developed to automatically gather outdoor weather data from Weather Underground website with 5-minute granularity. And files are created for every variable and are sent to the IoT Azure platform provided by IDP to be later used by iPredict or any other tool that may request it.
iPredict.
The first step consists of selecting the variables that are relevant among sensor data, but also derived variables obtained by aggregating, averaging, shifting, basic variables. The second step consists of selecting the machine learning technique to implement the algorithm and its associated parameters. This is an iterative process using different techniques and search algorithms. The last step is the creation of a model. It consists of a bunch of transformation to the input variables to generate the target variable. A good model is the one capable to produce values that approach very much real measures. The principle is to detect deviations between estimated and measured energy consumption. Abnormal values are likely to respond to a malfunction in the system. In this pilot, iPredict analyzes the heating and cooling facilities. A request is triggered to fetch the latest sensor data from the IoT platform. To assure a good data quality for the algorithm, another process cleans the data to get rid of outliers and populate missing values, as well as resampling and aligning at convenient time resolution. This clean data is sent back to the IoT platform using a web service for later usage. Very early in the morning, the algorithm estimates the electrical and thermal consumption. The deviation between actual and estimated values allows to estimate the degree of severity of the incidence. This is the output of the iPredict tool. The output is sent to Sphere ecosystem. The IoT platform receives actual and estimated energy consumption, and deviation. IMAN maintenance tool receives a notification containing the severity of the deviation and the energy consumption values. This notification will be sent by email to the facility manager, who, if necessary, will analyze the recorded data in more detail.
IMAN.
The data calculated by the ML model is then converted to an alert in the predictive maintenance tool, IMAN. The maintenance manager can decide if this alarm could be caused by an abnormal performance of the facility. If he approves the alert, a work order is automatically generated with the goal to repair the fault in the equipment. As soon as the reparation is executed, the user can fill additional information, like costs or documents, and he can finally close the work order. This way, the workflow is ended and the work order is saved in the database for future analysis.